Hello, everyone. Hi, do you hear me?
Yes,
Good
Professor.
afternoon.
Yes, I do.
Sorry that we moved to the online because there is some issue in our classroom. I think is something like related to CO2 or something. So because your health is very important, this is why they moved it to online this time. Most probably they will assign another room for us, and I will let you know what is the room and in which building. Okay, so if you are able to open your camera and say hi to your classmates, it will be great. If you cannot do that, it's fine. You can unmute yourself and say hi.
Hi.
Hello.
Hello.
Good afternoon, everyone.
Okay, guys. So today I'm planning to finish chapter 2, and we'll see where we stopped, and then finish part 1, and then go over part 2. So we'll finish chapter 2. And if you have any question at any time, please stop me at any time. Just unmute yourself and ask the question you have at any time. Okay? So let me set up my computer because I will write on the screen, and then we'll start.
Professor, do we have a homework due this coming Sunday?
No, there is no homework. Enjoy your time.
Okay, thank you.
Sharing. Let me share slides. It's part 1. Second. So again, please, if you have any question at any time, please let me know. Just unmute yourself and ask the question at any time. So let's see where we stopped. We stopped at the confidence interval for the difference between two population means or between the two treatments, mu1 minus mu2. So sometimes we are not interested in mu1 equal mu2 against mu1 greater than or less than or doesn't equal mu2. Sometimes we are interested in the difference, the value, the difference is what? So mu1 minus mu2 is what? Mu1 minus mu2 is between what two values? I'm interested in lower limit and upper limit of that difference. So sometimes we are not interested in they are equal or not because we are interested in the value of the difference itself. So in general, the confidence interval for the difference between two treatment means is y1 dot bar minus y2 dot bar plus or minus t value at alpha over 2 and degree of freedom n1 plus n2 minus 2 times the pooled standard deviation is p as a common factor because we assume sigma 1 square equals sigma 2 square times 1 divided by n1 plus 1 divided by n2. So this one plus this one, it gave me the upper limit. This number minus this number will give me the lower limit. You see, you know all these values. 1 second. So you know all the values. You know y1 dot bar, y2 dot bar, you know SP already calculated before, you know n1, you know n2. The only number you don't know is t value is what? So how do I calculate t? You don't need to calculate t, you need to find from the t distribution table. So you need to calculate alpha over 2 is what? Alpha is 5%. 5% divided by 2 is 0.025. And degree of freedom n1 plus n2 minus 2. So 6 plus 5 is 11. 11 minus 2 is 9. So now you go to the t distribution table and find the t value is what? Find degree of freedom first column, 0.025 first row, and U intersection is the t value. So let me show you how to find them. Let's go to our Canvas page, because I already uploaded the t distribution and the distribution. So when you click on this one, the first 2 pages for the standard normal distribution, and the last page is for the t distribution. The first column is degree of freedom. My degree of freedom is 9. And alpha over 2 is 0.025. So the intersection is 2.262. This is the t value. So now you have everything in the confidence interval. Plug in all these values in the confidence interval. You get lower limit and upper limit of the confidence interval for mu1 minus mu2. So let's go back to our slides. So now we know the t value is what? We already calculated SP before in test of hypothesis. You know N1, you know N2, you know Y1 dot bar, Y2 dot bar from the numerical summary. This one is N1. This one is N2. This one is Y1 dot bar. This is Y2 dot bar. This one is S1 squared. This one is S2 squared. This one is S1. This one is S2. The sample standard deviation for the second group or for the second treatment, which is the second fertilizer. So I can plug in all these information or these values in this formula. I get lower limit and upper limit. You plug in the values Y1 dot bar minus Y2 dot bar, t value, and SP square root 1 divided by N1 plus N divided by N2. And you get the lower limit is negative 10.31, upper limit is 6.65. This is the 95% confidence interval for the difference between mu1 and mu2. So it means if I did the experiment in a very long scale, like I assign many plants to the first fertilizer, and many plants to the second fertilizer, and I calculate mu1, I calculate mu2, I calculate the difference between mu1 and minus mu2. That difference will be between negative 10.3 and 6.65 with 95% confidence level. Can I use this confidence interval to decide which one is correct? Like H0 is mu1 equal mu2. H1 is mu1 doesn't equal mu2. Can I use the confidence interval to test, to decide which one is most probably correct? Can I use the confidence interval to reject or fail to reject H0? You can do it. In general, if the lower limit is positive, upper limit is positive, you conclude that mu1 is greater than mu2. It means mu1 doesn't equal mu2, so you reject H0. If the lower limit is negative, upper limit is negative, you conclude that mu1 is less than mu2, so you reject H0 because they are not equal. But if the lower limit is negative, upper limit is positive, it means 0 is one of the possible values for the difference between mu1 and mu2, so you conclude that mu1 equal mu2, so you fail to reject H0. So our confidence interval, lower limit is negative, upper limit is positive. So we fail to reject H0, which is the same conclusion from the test of hypothesis. It means mu1 equal mu2 at significance level 5%, the complement of the confidence level. So at significance level 5%, the two types of fertilizers are the same in terms of yield. There is no difference between these two. So this is how to calculate a 95% confidence interval. Do the same thing with 99. We change only the t value. So now I need to know how to do the confidence and test of hypothesis and the confidence interval using OR. So you need to know what is the function you should use? As I said before, after I finish chapter 2, I will go over all these code and we'll practice together one more time because I want you to be expert in all. So the function you should use is t.test. This is a t-test function, can be used to test mu1 equal mu2 versus mu1 is greater than mu2 or mu1 less than mu2 or mu1 doesn't equal mu2. So you give the first group of data, the values for fertilizer A, second group of data, values for fertilizer B, and we assume the sigma 1 square equals sigma 2 square. How do I let R knows that I assume sigma 1 equals sigma 2 square? Variance equal this, this option, it should be true, the equal variances. So your first group, comma, second group, comma, and then the assumption. And then save everything under some name, any name, and then print what is saved. See, it gave me T0 is almost the same value we calculated by hand. Degree of freedom is 9. P-value is 0.63 as we calculated using the applet. And the alternative hypothesis in R is mu1 minus mu2 equals 0, which is equivalent, mu1 minus mu2 doesn't equal 0, which is equivalent to mu1 doesn't equal mu2. So this is the alternative because this is the default for the t-test function. Can I change it? You can change it. I will show you how to change it. And the lower limit of the 95% confidence interval, the upper limit of the 95% confidence interval, this is y1 dot bar, this is y2 dot bar. This is the output from R. So I can use this p-value to test H0, mu1 equal mu2, or you can write it down as mu1 minus mu2 equals 0, versus they are not equal 0. So when I look at the p-value, I see it is greater than alpha. So I fail to reject H0. So I conclude that mu1 equal mu2 at significance level 5%. So this is the function you should use to do the t-test to compare two treatment means. Any questions so far? Any questions so far?
Yeah, Professor,
Okay.
quick question.
Yeah, sure. Sure.
So why do we assume equal variances again in this case?
That's a very good question. I'm going to cover the two cases. I'm going to cover the equal variances case and unequal variances case, and then I will let you know which one you should go with. So far, we covered only a rule of thumb. Rule of thumb said, divide S maximum by S minimum, because you have two standard deviation. Divide the big one by the small one. If this ratio is less than 2, assume equal variances. If this ratio or S square maximum divided by S square minimum less than 4, you assume equal variances. When we divided S maximum by S minimum is 7.03 by S minimum 5.4. This one divided by this one is less than 2. So we assume the sigma 1 equals sigma 2 squared. Got it?
Yep, thank you.
You're welcome. But I will cover the second case just in case, to practice, only for practice. I will cover the other case, which is sigma 1 squared doesn't equal sigma 2 squared. Because keep in your mind, the rule of thumb, it's not that much formal. I will show you some formal tests for equal variances, and that test will decide which case we should work with. Sigma 1 equals sigma 2 or sigma 1 doesn't equal sigma 2 in a few minutes. So if you do not have any questions, so let's cover the second case, which is sigma 1 squared doesn't equal sigma 2 squared. We need to know what will it change. The test statistic, will it change? And degree of freedom, will it change? And we will see anything else, will it change or not. If you see that sigma 1 squared doesn't equal sigma 2 squared, if you assume this. So the second case, which is unequal variances, sigma 1 squared doesn't equal sigma 2 squared. Let's see the statistical model, will it change or not? Yij equal mu I plus epsilon ij. I is 1 and 2, two treatments, two fertilizers. J is 1 up to Ni. Nothing changed so far. The only changes now epsilon ij doesn't follow normal with 0 and sigma square. It follows normal 0 with sigma I square. It means I'm assuming sigma 1 square. The variability for the first treatment is different from the variability of the second treatment. The data for the fertilizer A is different from the data. The variability in fertilizer A data is different from the variability in fertilizer B data. So the statistical model will be the same, but we will change the variability to be different. H0 is the same, H1 is the same, and then T0 is Y1 dot bar minus 2 Y2 dot bar divided by S1 squared divided by N1, S2 squared divided by N2. Now we do not have the same variability. I cannot take S squared as a common factor because we have two different variances. So the test statistic will change. There is no SP. Also, the degree freedom will change. We do not use the degree freedom N1 plus N2 minus 2. If you assume sigma 1 square equals sigma 2 square, the way you calculate degree freedom is easy. N1 plus N2 minus 2. But if you assume sigma 1 square doesn't equal sigma 2 square, you need to use this formula for the degree freedom. So based on the assumption, the degree freedom will change. So maybe the decision will change because the p-value depends on the degree freedom. So maybe the decision will be different, or the decision will be the same. Let's see. So we need to calculate the degree freedom using this big formula. I know this is very big. The guy who came up with this formula, I think his name is Satterway. And he said this formula is much better than this one if you assume sigma 1 square doesn't equal sigma 2 square. Let's see what else will it change. This is step number 1. Step number 2, significance level. Step number 3, you calculate the test statistic value, plug in the values, and I got negative 0.48. The fourth step, you calculate p-value, but before you calculate p-value, you need the degree of freedom. Degree of freedom is 7.49. You always round it down. Why? Because it is more safe to work with a smaller degree of freedom. It is 7.49, I will make it as 7. If I got 7.6, I can round it down to be 7 also. So it always round it down because it is more safe to work with a smaller degree of freedom. And then I need to get the p-value. Let's use the applet one more time. If you go to the applet, why you do not use the t-distribution table? Because actually t-distribution table doesn't work most of the time because it doesn't give me an exact value for p-value. It gave me a range of values. So sometimes it doesn't work. So let's use the applet, or you can use R, you can use some advanced calculator, or use some other software, it's up to you. So the degree of freedom, because the applet will ask me, what is your degree of freedom? The degree of freedom is 7. And it will ask me, what is the T0? T0 is negative 0.48. And it would ask me, the alternative hypothesis sign is what? It is doesn't equal. So let's give these 3 information to the applet, and it will give us the p-value. Share it. Do you see my screen?
Yes.
Guys, do you see my screen?
Yes.
Hello. I entered degree freedom equal 9. Do you see the 9?
Can you not hear us, Professor?
Do you see my screen? This one?
Yes.
Okay. The degree of freedom is 9. And my T0 is negative 0.48, I think. 48 or 49? T0 is 48, negative 0.48 or negative 0.49?
It's negative 0.48.
Thank you. The third information you should give is doesn't equal, so I selected the third one. If the alternative is greater than, use the first one. Alternative is less than, use the second one. Alternative doesn't equal, use the third one. So this is the p-value. It's still big. 0.64. So I will fail to reject H0 again. So let's go back to our slides. The p-value is big. So now I compare p-value to alpha. It is greater than 5%. So my decision is fail to reject H0. So there is no enough evidence to reject the null hypothesis. It means the standard fertilizer mixture and the improved one are the same in case we assume different population variances. And you know, also you need to say at 5% significance level. So the two fertilizers are the same in terms of the mean, the yield, assuming sigma 1 squared doesn't equal sigma 2 squared. So you need to mention all the assumptions. So this is our decision. So when we use the sigma 1 equals sigma 2 squared, our decision was fail to reject. When we use the sigma 1 squared doesn't equal sigma 2 squared, we fail to reject. Sometimes the decision will change. So which one I should use? I should use sigma 1 squared equals sigma 2 squared, or sigma 1 squared doesn't equal sigma 2 squared. It depends on the rule of thumb, or you can do a test. I will show you some tests. But after we calculate a confidence interval for mu1 minus mu2 under unequal variances. So let me write down the formula. The only change is what? Is we do not have SP. So assuming sigma 1 squared doesn't equal sigma 2 squared, our formula is y1 dot bar minus y2 dot bar plus or minus t at alpha over 2, and degree of freedom, in this case is 7, is different from the previous one, times the square root S1 squared divided by N1 plus S2 squared divided by N2. Y1 dot bar is 20.7 minus Y2 dot bar is 22.53 plus or minus. Go to the table and find 0.025 again, but degree of freedom 7. You will find the value is 2.365. It changed a little bit. Times the square root of S1 squared is 49.42 divided by 5 plus 29.51 divided by 6. And this one minus this one gave me lower limit. Lower limit is negative 10.93. This one plus this one gave me upper limit 7.26. So this is the lower limit and upper limit of the confidence interval of mu1 minus mu2 at significance at confidence level 95%. And I see the lower limit is negative, upper limit is positive. So again, I conclude that mu1 equal mu2. So we fail to reject H0. If you'd like to explain these two values, so you can say with 95% confidence level, the difference between the two means mu1 minus mu2 is between negative 10.93 and 7.26 at 95% confidence level. This is the meaning of the confidence interval, and this is how to use the confidence interval to do test of hypothesis. So we fail to reject H0 because the lower limit is negative, upper limit is positive. Any questions so far? Please, if you have any question at any time, unmute yourself and ask me your question at any time. So how do I do the test and the confidence interval when I assume sigma 1 squared doesn't equal sigma 2 squared? Use the same function, t.test. Give the first group of data, second group of data, but variance equal is false. It means sigma 1 squared doesn't equal sigma 2 squared. So it gave me T0 again. It gave me degree of freedom 7.48, approximately 7. It gave me p-value. I use the p-value to take my decision. I see p-value is greater than 5%, so we will fail to reject H0. And the alternative hypothesis is the true difference is not equal 0. So H1 mu1 minus mu2 doesn't equal 0. This is H1. Oh, sorry, this is H1. Oh, sorry, H1 is the alternative. And H0 is mu1 equal mu2. Or you can write it down as mu1 minus mu2 is 0, the difference is 0. And it gave me 95% confidence interval. This is the lower limit, and this is the upper limit. And it gave me y1 dot bar. It gave me y2 dot bar. So I use the same function again, t dot test, but I use var equal variances, equal false. It means I'm assuming the variances are not equal. So what is the rule of thumb for equal variances? Again, as I said, S maximum divided S minimum should be less than 2 to assume sigma 1 square equals sigma 2 square. Otherwise, assume sigma 1 square doesn't equal sigma 2 square. But we need to cover a test. I will show you some tests because the test is better than rule of thumb. So what are the assumptions? Because keep in your mind, we said mu1 equal mu2. The two fertilizers are the same in terms of yield at significance level 5%. But before this conclusion, you need to check the assumption. Because every test in statistics has some assumptions. If the assumptions are satisfied, you can conclude. But if the assumptions are not satisfied, you need to fix the problem of the assumptions first before you do the test, before you make any conclusion. So we need to wait a little bit. We are not going to say they are equal unless the assumptions are satisfied. So let's see the assumption. The first assumption, the two samples are independent. We have two samples. The first sample assigned to fertilizer A, second sample is fertilizer B. The first one received the 5 plants. The second one received 6 plants. These two samples are independent because these 5 is completely different from these 6. Can be the same, they can be the same. So because sometimes the two samples are dependent. We have only one sample of individuals, but we measure the sample twice. This is part 2. I will cover this one in a few minutes. But our assumption is satisfied. We have two samples are independent. The second assumption, the two samples are randomly selected from normal distribution. How do I know? The first group of data, 5 values. Second group of data, 6 values. I need to make sure each is randomly selected from normal distribution. You look at the histogram of each, but the histogram doesn't work because the sample sizes are small. Look at something else. Let's look at the box blood. The box blood is fine, but still the sample is very small. Look at the normal probability. The normal probability blood is better than histogram, better than box blood. I need something much, much better. Do the test. Let's do normality test. So let's look at normal probability blood first and then do the Shapiro test. That test is much better than graphs. So how do I graph the QQ blood? You use the QQ norm function, give the group of data, and then use the QQ line, give the data. Let's see the output. So this is the data for A. And QQ norm function, this one gave me these dots, these circles. If these circles are making a straight line, it means normality is satisfied because in this graph, they compared your data to the standard normal data. If your data follows normal, it should make, the points should make a straight line. The dots should be very close to the straight line. So let's graph the straight line, QQ line. It gave me this line. And I see the dots are very close to the line. It means normality is satisfied for A. But the test is much better than QQ blood. But QQ blood is better than histogram in the box. And then I graph the second. Oh, I gave A again. I should give B. So this one should be B. This one should be B. Sorry, guys. I should have another graph for B because it looks like they are the same. I'm sorry for this one. I will change this one to be B. But for sure, I know I looked at this one, but looks like I take a wrong screenshot. But it is satisfied. So let's look at something better than the QQ plot, the normal probability plot. So looks like from these, if this one is B and this one is A, looks like the normality is satisfied in both of them. But let's look at the Shapiro test. What is the function I should use to do a Shapiro test to check normality for some data? The function is Shapiro.test and give the group of data, yield A, and I give you some output. Do the same thing for B, give you some output. The very important number is this one, p-value, because I use p-value to decide the normality is satisfied or not. Because R should give me the null hypothesis and the alternative hypothesis, but I don't know, because I don't know why the guy who wrote this function, Shapiro.test, he didn't give us information about the null hypothesis and the alternative hypothesis for this test. But it is always that H0 for Shapiro test, normality is satisfied. It doesn't change. H1 always, normality is not satisfied. And then I use p-value. I need to have a big p-value to fail to reject H0, to assume normality is satisfied. My p-value is 0.95 greater than 5%. So we fail to reject H0. It means normality is satisfied for group A, for the data of the fertilizer A. Let's do the same thing for B, this one for B. Again, H0 is the same, always Shapiro test, null hypothesis is normality is satisfied. H1, normality is not satisfied. I need p-value to be big. P-value is 0.55. So p-value greater than 5%. Sometimes you use 10%, but whatever 10% or 5%, normality is satisfied. So normality is satisfied. So now I can assume the two groups of data comes randomly selected from normal distribution, and the assumptions are satisfied. So this conclusion is correct, that mu1 equal mu2. But I used the rule of thumb to decide sigma 1 square equals sigma 2 square or doesn't equal. Can I do a test to make sure which one I should go with? I know both of them gave me the same conclusion, but sometimes gave me different conclusions. So I would like to know which one I should go with. You should do a test for equal variances. There is a test for equal variances, is called var.test. So this is the function you should use to test equal variances against unequal variances. So var.test gives the first group of data, comma, second group of data. This is a typo. So var.test yield A, yield B, and save under any name. You should use the name and then print is the name. It gave me p-value. So you need to know how to use the p-value to decide the equal variances against unequal variances. So our H0 should be sigma 1 square equals sigma 2 square versus H1 sigma 1 square doesn't equal sigma 2 square. I need to know which one is correct, which case I should go with. So the default is what? Alternative hypothesis, true ratio of the variance is not equal to 1. So this one is H0 or H1. This is the alternative hypothesis because this one can be rewritten as sigma 1 square divided by sigma 2 square is not 1. And this one can be rewritten as H0 sigma 1 square divided by sigma 2 square is Come on, 1 second, please. Step. Sigma. If there is something. Freeze, the sigma 1 square divided by sigma 2 square equal 1. Second, please. No, it doesn't. So 1 second. Let me stop sharing and see what is the problem. 1 second, please. Looks like my computer freezed, but give me 1 minute to ask my computer to work, please. Let's see. Let me write down H0 and H1 again. Sorry, guys. Oh, doesn't work again. There is something. One second. Do you see my screen, guys?
Yes.
Okay, great. So let's try. I hope it works this time. H0, okay. H0, sigma 1 square divided by sigma 2 square equal 1 against H1. Sigma 1 square divided by sigma 2 square doesn't equal 1. So can be written like this one. So this is the alternative hypothesis for R. And p-value is big, so we go with this one. So now we can go with the conclusion of sigma 1 square equals sigma 2 square, because the test confirmed that sigma 1 square equals sigma 2 square. And this is the lower limit and upper limit of the confidence interval of sigma 1 square divided by sigma 2 square, if you are interested. And this is the sample ratio, S1 square divided by S1 square divided by S2 square. So again, we covered case sigma 1 square equals sigma 2 square, and another case sigma 1 square doesn't equal sigma 2 square. I know both of them gave us the same conclusion, but sometimes gave different conclusions. Which one we should go with? The one the VAR test decide. The VAR test decide that sigma 1 equals sigma 2 square, so I go with the conclusion of equal variances. Any question about the part 1? Okay, if you do not have questions about part 1, let's go to part 2, which is dependent samples. So let's open the second file. I already uploaded this one on Canvas. So let's see. The pair DT test, and then we need to check the assumption, and we need to know the assumption about what, because the assumptions are very important. Before you make any conclusion, you need to look at the assumption. Let's see the assumptions are the same or different. So this is the second case. Let me give you an example. Let me give you 1 minute. Read this one, and then I will go over this one with you. So read this one, please.
We still see your file explorer, Professor.
So you do not see my file? Let me share it again. You see my screen? This one?
There you go.
Okay, thank you so much for letting me know. So please read this one. So the idea is we have two taps. This is one, the second one looks like two treatments. And our research hypothesis is, are the two tips different, or one of them is better than the other in terms of the depth or in terms of hardness? So we have a machine and we have some specimen. So how do I run the analysis? How do I design my experiment? You can design the experiment as a complete randomized design, or you can design your experiment as a complete randomized block design, or paired design. So let me show you what do I mean. You can make it as the one we covered in part 1, like a number of metal specimen, let's say 20, could be randomly assigned to the two taps. Half of this specimen could be tested by tip 1, and the other half could be tested by tip 2. This is a complete randomized design, and the two samples will be independent. The idea is we'll have two treatments, treatment 1, treatment 2, or tip 1, tip 2. And I will assign some specimen to the first one, like maybe 10 or 20. And I will assign some specimen to the second one, maybe 10, 20. Can be equal, can be unequal. And then measure the hardness, and then compare the two means, and run t-test as we did in part 1 and then done. But the problem is this specimen may be different terms of hardness. So suppose the metal specimen were cut from different bar stock that were produced in different heats that might affect the hardness. This lack of homogeneity between the specimen will contribute to the variability of the hardness measurements and will tend to inflate the experimental error, sigma squared, thus making a true difference between the tips harder to detect, because the variability, the total variability, or the experimental error will be very big, because there are many sources of variability. A source of variability due to hardness, due to different specimen, and variability due to many other random variables. So we need to take some variability from the experimental error that is due to differences between the specimen. So decrease the variability of the experimental error. So to protect against this possibility, assume that each specimen is large enough so that two hardness determination may be made. And then you randomly assign one tip to one half and randomly assign and the second one to the remaining half. What do you mean? I mean, now I have two tips, tip 1 and tip 2. And I know these specimens are different. What should I do? You should do a paired t-test to decide, not the two independent sample t-test. So each specimen will be divided into two parts and randomly assign one of the tips, like maybe this one is tip 1, this one is tip 2. Maybe randomly assign, maybe this one will be tip 2, this one will be tip 1, using a coin. So the last one, tip 1, tip 2. And now you will have a group of data for tip 1, group of data for tip 2. But keep in your mind, each pair comes from the same specimen. So this group of data and this group of data are dependent, not independent. So the first specimen, assuming give us tip 1, 7, tip 2, 6. So the last one, number 10, give us tip 1 under tip 1 give me 4, under tip 2 give me 5. So these two groups of data are dependent because they come from the same specimen. So I shouldn't work with these as two independent samples. I work with the difference. You calculate the difference. 7 minus 6, 1, 3 minus 3, 0, 3 minus 5 minus 2. So the last one, 4 minus 5 minus 1. And work with this group of data. Do not work with step 1 group data or the step 2 group of data. Work with the difference between the two steps to test they are equal or they are different. So let's see the statistical model, will it change or not? The statistical model will change because it will be Yij equal mu I plus beta j. This is the effect of the specimen So specimen effect. This is the specimen effect. Because we need to take some variability due to differences between the specimen. And I is still from 1 to 2, j is from 1 to 10. It is not ni because they have the same number of values. So the first group has 10, second group has 10. And we're gonna work with the dj, the differences, not y1j or y2j. This is the difference between y1j, y2j. We need to have this statistic as unbiased estimator for the difference. So let's calculate the expected value of dj. The expected value of dj equals expected value of y1j minus y2j equals expected value of y1j minus expected value of y2j. The expected value of y1j is mu1 plus beta j, and this is the expected value of the second one. Beta j cancel with beta j. It's what mu1 minus mu2. So mu d is an unbiased estimator for the difference between mu1 minus mu2. So if I test mu d equals 0, this one is equivalent to mu1 minus mu2 is 0. Against h1, maybe mu d is greater than or less than or doesn't equal 0. So the dj is unbiased estimator for the difference between the two population means. So let's go over the 5 steps. The first step, for testing the two tips are the same or they are different. Write down the null hypothesis and the alternative hypothesis. Mu d is 0. Mu d is not 0 or greater than or less than. It's up to you as a researcher which one you select, which one is you are interested in. Let's go with the difference. The second step, determine the significance level alpha. Let's use 5%. The third step, you calculate this statistic T0. It is d bar divided by SD divided by square root of n. What is d bar? D bar is the average of the differences. So sum of d divided by n. What is the SD? The standard deviation of the differences. Do you remember the standard deviation of x is 1 divided by n minus 1 times sum of x squared minus sum of x all squared divided by n. Change x to be d, will be 1 divided by n minus 1 times the sum of d squared minus sum of d all squared divided by n. So I need sum of d squared, I need m to be able to calculate d bar SD. So, and then I will calculate p-value using the applet as before, and the degree of freedom is very simple, number of pairs minus 1, n minus 1. And then you take a decision. So let's practice on this one for our data set. This is the values for tip 1, this is the values for tip 2. And then you calculate the difference between these two groups of data. So this one is the sum of d, and then you square all these. 1 times 1 is 1, 0 times 0 is 0, negative 2 times negative 2 is 4. And this one will be the sum. This one is sum of d. This one is the sum of d squared. Now I can calculate the average. Sum of d divided by n is negative 0.10. This sum s of d is the square root of 1 divided by n minus 1, 10 minus 1. Sum of d squared is 13, sum of d is negative 1, n is 10. Now I can calculate SD. So now I have d bar and I have SD. Now I can follow the 5 steps, these 5 steps, because I have all the unknown values. So let's follow the 5 steps to see tip 1 equal tip 2 or on average, the average of the hardness. Or they are different. So let's follow the 5 steps. The first step, guys, if you have any question at any time, please let me know. Unmute yourself and ask me the question at any time. H0, mu d is 0 versus H1. Mu d is not 0. Second step, alpha, let's use 5%. Third step, calculate T0. It is d bar divided by S d divided by square root of n. We already calculated d bar is negative 0.10 divided by SP is 1.197 divided by square root of 10. This value is negative 0.26. And then I will calculate p-value using the applet. The applet will ask me 3 information. It will ask me, what is your T0? It is negative 0.26. What is your degree of freedom? My degree of freedom is m minus 1. It is 10 minus 1, 9. What is the alternative hypothesis sign? My alternative hypothesis sign is doesn't equal. So now I can go to the applet and give me the p-value. Let's click on the applet again and find p-value. And let me share it. So now let's nu or v is the degree of freedom. Degree of freedom is 9. X is the T0. T0 is negative 0.26. And the alternative hypothesis is doesn't equal, so I will select the third one. So the p-value is 0.8, is very big. So looks like I will fail to reject H0. So let's go back to our slides. P-value is 0.8. So the last step, take your decision. P-value is greater than alpha, which is 5%. So we fail to reject H0. It means the two steps are the same in hardness at 5% significance level. This is how to do a test for using the paired t-test. So how do I use R? Should I use a different function? Different from the t-dot test? Use the same function again. T-dot test. And this is in general. You give X, you give Y. The alternative can be two-sided, can be less than, can be greater than. The mu to test mu equals 0. Or the difference between the mu's is 0. You can make paired or not. So the default is false. It means the two samples are independent. But you can change it to be dependent. You make this one true. And variance equal can be false, can be true. Confidence interval you change, and so on, so on. So let's do our test, 30 tests for our data. Tab 1 data, tab 2 data. Use t-test, give the first group of data, second group of data. Let's use alternative two-sided. I know it is the default, two-sided, but let's write it down. The new one is this one. Pair this true. The data is dependent data. So our function will calculate tab 1 minus tab 2, calculate the d, then calculate d squared, then calculate d bar, calculate SD, and so on. So it gave me T0 as we calculated. It gave me degree of freedom, n-1. It gave me p-value is almost 0.8. So using the p-value, now I can take my decision. H0 is mu d equals 0. What is H1 or HA for the R function? Alternative hypothesis, the true difference is not 0. So mu d is not 0. And this is 95% confidence interval for the mu d. Mu d is between negative 0.956 and 0.756. And it gave me the estimation for d bar, already calculated this one, negative 0.1. So based on the p-value is big, so we fail to reject H0. So our conclusion is the two tips are the same in terms of hardness at 5% significance level. Again, we shouldn't conclude before check the assumptions. So let's see the assumptions and make sure the assumptions are satisfied. Do the assumptions are about the two groups of data? They are dependent and each is normally distributed, or the assumptions are on D, the differences. Let's see. There are two assumptions. The two samples are dependent. It means each individual or each experimental unit measured twice. So this is our case. That's correct. The second assumption is the differences D follows normal distribution with mean 0 and variance sigma squared. So I need to double check the normality assumption for the D. So how do I check the normality for D? Look at the histogram, but the histogram doesn't work because I have only 10 values. Look at the box plot. I know the box plot is better than the histogram. Look at the QQ plot. QQ plot is much better than those guys. And I can do Shapiro test. So let's look at all of them. Histogram is not good because the sample is small. The box plot looks like normality is satisfied because these lengths equal this length. But so looks like normality is satisfied. But I need to look at the QQ plot. Let's look at the QQ plot. When I look at the QQ plot, keep in your mind the graphs are not that much formal testing. This one looks like normality is satisfied, but let's see. when I look at this straight line, I see many values are far away from the straight line. So looks like normality is not satisfied. I'm not sure. So let's do a test. Shapiro test. P-value is small. So now H0, let's write down H0 again for Shapiro test. Normality is satisfied. H1, normality is not satisfied. My p-value is small, is smaller than 5%. Even if I use 10%, it's smaller than 10%. So we reject H0. It means normality is not satisfied. So what should I do? I shouldn't conclude that they are equal. I shouldn't conclude tab 1 and tab 2 are equal in terms of hardness unless I fix the problem of the assumption. So how do I fix the problem? This problem, I need to fix normality. There are many ways. One of them is try to find some transformation that make your data follows normal distribution. We will cover this one later. But now we cannot conclude the tab 1 and tab 2 are the same in terms of hardness. We need to fix the assumption. If we tried all possible ways and we couldn't fix the normality, you have to go to the non-parametric tests. But keep in your mind, non-parametric test has less power compared to the parametric test. So you should fix the normality problem first. Make your data follow normal distribution. So again, do you think the assumptions are met? The assumption of normality is not met because Shapiro test said normality is not satisfied. Paired comparison t-test is a special case from the complete randomized block design, which will be covered in chapter 4 in detail. I will release an ungraded survey. That ungraded survey has 10 multiple choice questions. I want to make sure that you understand the material in chapter 2. And because one of the goals of this course is that when you listen to some TV show and they are talking about some experiment, you should be able to understand what they are talking about. I remember this speech Dr. Fauci gave. He was talking about the two experiments, or two treatments, and he talked about two experiments. You should be able to understand what he was talking about. Placebo, control, p-value, enough sample size, and the decision, and these kind of things, significant level, and so on. So you watch this video, and then you take the ungraded survey or ungraded quiz to see you understand the chapter 2 or not. I will post the link on the news section in our main Canvas page. So this is the end of chapter 2. And we need to practice on R because some students are not familiar with R. So I need to go over all the code we have covered in chapter 2 and also practice on some real data set. Any questions, guys? Do you have any questions? Do you have any questions? Okay, if you do not have any questions, so I'm done for today. This is what I was planning to cover. So thank you so much and have a great day. See you soon in person.
Thank you.
Thank you.
Thank you. Thank you.
Have a good day.
You too.
Thank you.
Thank you.
Thank you. Have a good day. See you guys.